So we now have two formulas in general that we're focusing on. So we have our compounding some finite number of times per year, n, or if we compound continuously, we have this base that is approximately 2.718, right? That's an irrational number, e, but in general, we're thinking of it as a base greater than 1, right? So this e value, if you don't totally understand e, just think of it a number about 2.7. But in both these formulas, we have similar things. We have A is that compound amount or the future amount, or it might be called the amount after some time. P is that principal amount. Oh, that's a typo. I got to check that spelling. That's principal AL. That's the amount you start with. It's also going to be the y-intercept, right? Because it's the value you get when t is 0. So that's your starting value. Then R is the interest rate written as a decimal. And so the only difference between these two is here we have some finite number of compoundings, n. So n could be like monthly, n would be 12. Or if it's continuously, then we have e. So both of these are exponential, of course, since the variable, in this case time, is in the exponent. And that rate that we've been talking about for a while here, this rate is really the key to exponential growth, right? Exponential functions change at a constant percentage rate. That's that r, okay? And so if we look at some 4 different functions, so here we have 4 different functions that I've graphed in Desmos. 2 of them have continuous growth, and 2 of them are compounded a finite number of times. So here, the red and the blue both start with like $50, let's say, but we've got continuous compounding, but this one's got an R value of 0.025, so that would be R being a positive 2.5%, versus this one would be an R is a negative 2.5%. Oops, sorry, that's hard to read. Negative. The difference is negative versus positive. So as usual, if we have a positive R value, that's going to be exponential growth. So notice the red here is exponential growth starting at $50, and then it's increasing. Versus if R is negative, that's going to be exponential decay. Right? Remember, negative R values led to B values being between 0 and 1, or in this case, the R value just is in the exponent. Negative R values are going to be decay. So that's the blue. The next two, the green and the orange, start at $30. And again, we see here a difference between a positive R value, right, being positive versus a negative R value being decay. So the green is growth and the orange is decay. Okay, but let's connect all these ideas to what we were talking about in an earlier video. So we've already talked about what kinds of R values. So again, this was number 9 above, but let's do it again in terms of interest problems. So if we have a positive R value, right? So we're looking at this interest value. We've got this R value right here. So what does it mean to have an R value greater than 1? So that means that we're going to be adding some amount to 1, right? So if R is positive, then 1 plus R over n will be greater than 1. Right? So we're looking at a base greater than 1. 1 plus R over n. If R is positive, I'm adding something. That'll be a base greater than 1. That's going to be our exponential growth. Right? If, however, R is negative, right? So we've got some, the value of our car is losing money at a certain percentage, 10% a year, something like that. So if we're subtracting off some R value, now we're looking at a B value. We're taking 1 and I'm subtracting off some amount less than 100%. So the B value is going to be between 0 and 1. That's going to be our exponential decay. Right? If you take an R value that's negative, then 1 minus some percentage is going to be a value between 0 and 1. Right? Now, what about for continuous compounding? What happens when R values are positive? So notice that if R is positive, then we have e to some positive number. So think of an example like e to the 0.25t. So you've got 2.7 something being raised to the 0.25 power. That's still going to be a base greater than 1. Right? So this is still going to be exponential growth. But if R is negative, so if we have e to the negative 0.25t, for example, that's actually going to be a value between 0 and 1. And the way to see that is think of e to the negative r as being the same thing as, using this negative exponent property, this is the same thing as 1 over e to the r, or 1 over e all to the r power. So what used to be something greater than 1 is now 1 divided by something greater than 1. So it's going to be between 0 and 1. And so again, we've got our exponential decay. So that R value really will uniquely determine whether we've got exponential growth or exponential decay. And it doesn't matter whether we have continuous compounding or a finite number of compounds.